Welcome to Double E Masters. Magnetic field lines. Okay, so let us make one concept very clear. These should not be called as magnetic lines of force. Why is it so? Because we have studied one of the similar concepts like electric lines of force. But there are some dissimilarities between these two. Electric lines of forces can be generated from a stationary charge plus or minus q, but and also exerts force on a stationary charge. On the other hand, magnetic field lines neither can be generated from a stationary charge nor can apply force to a stationary charge. If the charge is moving, these magnetic field lines can apply force on the moving charge or current. So this this is to avoid simple confusion between the students. These should not be called magnetic lines of force. No author has mentioned like this magnetic lines of force. Everyone is calling it magnetic field lines. So let us keep in mind, do not call it magnetic lines of force because it is technically not correct. Okay, the purpose of this lecture is to study the properties of magnetic field lines. So first of all, let us introduce what it is, where it came from, why is it so, and then we go for the properties. So there is a definition of this. Very simple thing is, let us assume a magnet. Okay, assume a bar magnet is a simple geometry. I have compiled some diagram here, and also you can assume a coil. Why we are doing this, the magnetic field of these two is very similar. Okay, so you can assume a bar magnet or a coil, depends on you. So what is magnetic field lines? Let us assume a very small magnet, or let us call a monopole. Okay, this monopole will be known as test pole. Okay, so I am talking about a monopole. Mono, that means single pole. Okay, so let me make it very clear, monopole does not exist in real life. Okay, you cannot have a magnet only with north pole or only with south pole. I will explain to you it later, but this concept is just for the explanation. Okay, so let us assume a test pole which is having only a single pole. This is known as test pole, unit pole, or monopole. Okay, one more condition is here. This test pole magnitude must be very small compared to the main magnet. Okay, why is it so? If this test pole is very large in magnitude, the geometry of these lines can be disturbed by it. Therefore, this monopole should be very small in magnitude, so that this geometry should not be disturbed by it, and we should get a real image of these line as possible. Okay, so what is going on? This is a very simple definition, so let us read. When a unit magnetic pole, what you are going, unit, that means one in magnitude, which is very small, magnetic pole is free to move in a magnetic field. So if you are drawing this, there should be magnetic field of a bar magnet. I am writing here bar magnet, or you can call it coil. Then it moves along the direction of resultant force. Okay, when you put this here, let us assume it is north. The general convention is to assume north. If you want, you can go for south, but you have to alter the direction of all the arrows in the diagram. Okay, so if it is north and it is also north, so this will have a repulsion force. But as this magnet is very small, so it will move away. Okay, you cannot move this, no? So it will move away. So at every point, it will have a force on it, like that, like this. When this small pole comes here, it is north and it is south, so it will be attracted by the south pole. So it will go like that. Okay. So if we connect all the dots here above the path traced by this small magnet, we would have a lines. So an imaginary curved path formed by tracing unit pole is called magnetic field lines. So this is the definition of magnetic field lines. When a very small magnet, unit magnetic pole, sometimes known as test pole, is placed in a magnetic field of anything we can trace, like earth magnetic field can also be traced like this. So when it is free to move, the path from here to here, whatever path it is following, by connecting or tracing this path, imaginary path, this path is known as magnetic field lines. As you can see here, if you place a pole here, a monopole here, it will also go like that, and at some point it will be like this. Is okay? So this is the definition. A small magnet, the path traced by that small magnet in an external magnetic field is known as magnetic field line. Okay, so let us go what are the properties of these magnetic field lines. Okay, one more time I'm repeating this. This is a magnetic pole. This is not a charge. You cannot put a charge and have a diagram like this. Is that very clear? Therefore, the nomenclature is magnetic field lines. Okay. Let us go with the properties. Properties of magnetic field lines. So, what are the properties of this? Number one is magnetic field lines of magnet or a solenoid that is coil, forms continuous closed loops. Okay. So, let us stop here for a bit. What it is saying is these magnetic field lines are closed. That means they are not discontinuous at any point. So let us take this. This line is north and it is going like this. By tracing this path, you comes to south. But according to this statement, inside the magnet, these lines should be like that. So outside the magnet, the direction of magnetic field line is from north to south. And inside the magnet, the direction of these lines is from south to north. So this is one point you should learn from here. Inside a magnet, the magnetic field line direction is from south pole to north pole, while outside it is from north to south. Okay. Second most important thing, if we have a magnet like this, which have north and north. Okay. So the direction of magnetic field lines cannot be from here, cannot be from here. So a magnet cannot have two poles of similar polarity. By this statement, we are concluding that a magnet must have poles of opposite polarity. Is that very clear? Okay, now next, one more thing. Can a magnet have only one pole? If it is north, so where are the lines going? Because it should be close according to this statement. So this magnet is also not possible. Is that understood? So by this statement, we are concluding that a bar magnet or a magnet must have two dissimilar polarities pole. If one is north, another must be south. Also, we are concluding that a single pole does not exist. So, what about the test pole? This is just an imaginary concept to explain. Okay. monopoles does not exist in real life. Is that very, very clear? So by this single statement, this is very, very important properties of magnetic field lines. Okay. In this single statement, we can including that the magnet must have two poles of opposite polarity. Is that very, very clear? And also the direction of magnetic field lines inside a magnet is from south pole to north pole. These two conclusions are drawn from this single statement. Okay, let us go for this. This is unlike electric dipole where these lines begins from a positive charge and ends on negative charge or escape to infinity. So let us recall the electric lines of force where we have a very simple one charge, single charge. This single charge can also generate electric lines of force. If there is no negative charge in the vicinity, these lines would extend up to infinity. But similar case does not happen with the magnetic field lines. So this statement concludes that very simple thing is a magnet with a single pole does not exist, while positive and negative charges can exist separately. Okay, so I hope you understand this point. This is very crucial point in this line. Okay, let us go for next. Tangent to the field lines at a given point represent direction of the net magnetic field at that point. Okay, so let us understand with this with the diagram. If you're going like that, let us assume any point on the line and draw a tangent. So the direction of force at this point is like this along with the tangent. At this point is along with this tangent. Actually, what is going on? Due to this north pole, there is a repulsion force on this monopole, and due to this south pole, there is an attraction force on this monopole. These forces are existing at each and every point as long as the monopole is inside the magnetic field of this bar magnet. But what is going on? This statement is concluding that you can know the direction of net magnetic field at any point. What you have to do, just draw a tangent at any point. You can do this at any lines like this. Okay, so it will be like this. What is the net force on the magnetic monopole? This force is magnetic field. So we can say that the resultant force is the magnetic field. Therefore, by drawing a tangent, you can know the direction of net resultant force on monopole at that point or magnetic field at that point. Is that very clear? Okay. Go for the next point. This is important also. Let us explain here. Let us draw some area, imaginary area here like this. And let us put the same area here. Okay. Assume this area is 1 unit squares. Okay. This is also 1 unit square. What is going on? If you count the lines 1, 2, 3, 4, 5, 6, 7. 7 lines are passing through this area of 1 unit square. While the similar area is placed here, only 2 lines are passing through it. So, what is the conclusion here? If the number of magnetic field lines crossing per unit area is more, the strength of the magnetic field is more. Is that clear? So, in region 1 and region 2, I have named this region 1 and region 2. What is going on? The number of lines per unit area is more. So magnetic field B1 is greater than B2. Okay. The bar magnet does not have a uniform magnetic field. It is stronger in some areas, like here, and it is weaker in some areas, like here. So in this particular case, you can say that in the axial position, the magnetic field is stronger, while in the equatorial positions, the magnetic field is weaker for the particular bar magnet. For any other geometry, you can conclude this by seeing the magnetic field lines. Okay, let us go for the next point. Magnetic field lines repel each other in the direction along perpendicular to its length. Okay. Let us refer the diagram. A little critical it is. Okay, so what is going on? If we see in the region 2, like here and here, what is going on? The magnetic field lines are bulging out here. Here it is bulging out, here is a bulging out. So there are more magnetic field lines in between. We haven't drawn that. Whatever they are doing, they are repelling each other. If they're not repelling, they could be a straight line here. So magnetic field lines are repelling each other perpendicular to the length. So what is length? Length is here in this direction. Okay. So they are repelling each other perpendicular to the length. Okay. Let us go for another very important property. Magnetic field lines do not intersect each other. Okay. Do not intersect each other. So why is it so? Why they cannot intersect each other? How we can say that? So let us see a point. Let us assume the magnetic field lines intersect each other. For a moment, let us assume that. So let us call it line 1 and line 2. What we have learned from point number 2, that you can have a direction of a resultant force by drawing a tangent. Okay. Now, if point P is the point of intersection, you can draw a tangent like this, and you will have a resultant force like that. But also you can draw a tangent like this and can have a resultant force like that. So what happens? There are two resultant forces at a single point. So this is not possible. Okay. You will have only one resultant force. If you are experiencing 400 forces at a point, the resultant force will be single. There cannot be more than one resultant force. Therefore, magnetic field lines never intersect each other. Okay, this is very crucial point. If they are intersecting, these are not magnetic field lines. Is that very clear? So this should not intersect each other at any point, at infinity or anywhere. They cannot intersect each other.